ESD, the sudden transfer of electrostatic charge from one object to another. With lightning, each flash is an immense discharge of static electricity, from a thundercloud where it is built up into the earth below. Think about the crackling and sparks that occur when you remove clothes from a dryer. How about the shock you sometimes feel when you walk across a carpet and touch a doorknob? These examples of ESD, which we can see and feel, last for a fraction of a second and contain anywhere from about 2,000 volts, the lowest level most people can feel, to over 25,000 volts. However, below 2,000 volts, there is still enough static electricity to cause static discharge and damage electronic circuits even when we don't feel it. Still, we're generating static electricity all the time. And a lot of common objects around us can be sources of static electricity too. In fact, for some devices, static zaps under 20 volts are capable of damaging or destroying the sensitive electronic components we handle every day. That transfer of static electricity, whether visible or not, is called electrostatic discharge, or ESD. So we can better understand what we're dealing with, let's examine the basic physics of static electricity, the primary cause of ESD. Electrostatic charge is created by contact and separation of materials. This phenomenon is known as triboelectric charging. It involves the transfer of electrons between materials. The resulting charge on a material may be positive, negative, or neutral. If one examines the smallest particle of a material, the atom, one sees that protons are positive and reside inside the atom's nucleus. Electrons are negative and orbit at high speed around the outside of the nucleus. When any two materials are placed in direct contact and then are separated, negatively charged electrons are stripped from the surface of one material and transferred to the surface of the other material. Now, both materials are charged with static electricity. When there is an imbalance of electrons on the surface of a material, an electrostatic charge exists. The symptom of a static charge is an electrostatic field. This field can be measured and can influence other objects in the near vicinity. People are a major potential source of ESD. That's because our bodies easily accumulate static electricity. In fact, our bodies can store relatively large amounts of this electrical charge. Let's begin by taking a look at what equipment is available to reduce the risk of ESD damage from people. The idea is to drain off charges in a controlled manner before they reach the devices. To do that, our bodies need to be connected to ground. If a charged ESD-sensitive device comes into contact with a static dissipative surface, this contact safely channels the charge away from the ESD-sensitive devices and drains them into the earth or ground. There are several methods used to drain off charges that we might carry into an ESD-safe area, or that we may generate while doing our jobs. The most common are the wrist strap and the shoe grounder. We'll take a look at the wrist strap first. Wrist straps are very effective for any operation where people are seated at their workstations. They are also effective for standing operations that don't require much movement. Shoe grounders are not as effective when seated because people may raise their feet and lose contact with the static control flooring. The wrist strap needs to be worn snugly against bare skin. It should be attached securely to a ground wire with a current limiting resistor and some form of quick connect disconnect. The current limiting resistor in the wrist strap cord limits the current flow through this intentional path to ground if the wearer comes into contact with sources of live power. To avoid ESD and safety problems, long hair needs to be restrained with hair ties, pins, or a hairnet. Once you've tied up your hair, you may still need to secure it to keep it from moving around. You can place it inside your smock or fasten it to the back of your head. Loose clothing can also be a safety and an ESD hazard. Long folds of clothing moving around can create static charges, get caught in equipment, or just plain get in your way as you work. As obvious as it sounds, soldering irons are quite hot, sometimes at temperatures nearing 800 degrees F. The heated tips can cause serious burns after being in contact with your skin for a fraction of a second. They can easily burn through your clothing as well. Pick up soldering irons by the handle only. A soldering iron should only be in your hand when you are actually using it to solder. Never use one as a screwdriver or scraper, or worse still, as a pointer in a conversation. To remove excess solder from the iron, wipe the tip on the cleaning sponge. Avoid flipping the molten solder off the tip. During soldering, the smoke or fumes which are created contain a mixture of noxious gases, including formaldehyde and hydrochloric acid. Soldering workstations should be well ventilated or equipped with some form of local exhaust ventilation or LEV. An LEV will remove the solder smoke from your breathing zone and vent it away, leaving clean air for breathing. Lead-free solders are commonly used for hand soldering these days, which reduces potential exposure to lead. Although some companies still use tin lead and lead-free solder for different product types. It's best to practice common safety precautions regardless of the type of solder you might be using. Ingestion is the most likely form of exposure to lead during electronics assembly. To avoid ingesting lead, never bite off solder wire with your teeth. Gloves are recommended for handling tin lead solder wire or solder paste. One common way of accidentally ingesting lead is touching food, cigarettes, chewing tobacco, or makeup after handling tin lead solder or solder paste. To avoid this problem, always wash your hands in soap and water before touching any item that will come into contact with your mouth or nose, such as food or cigarettes.
Each type of component is identified by a specific letter or reference designator. For example, the letter U is for an IC. Resistors and capacitors are identified by the letters R and C. It is important to learn these symbols so you can identify components. Axial components are parts such as resistors and capacitors that have only one wire or lead coming out of each side.
Chip components are typically ceramic, glass, or alumina-bodied packages with metal connections at either end, called terminations. These component types typically include resistors, capacitors, diodes, and inductors. Let's begin with flat rectangular chip components. These are the most common chip component style. The metallized terminations on the ends of the chip resistors will typically wrap around 3 sides of the component, or cover all 5 sides, as is the case for chip capacitors. Chip components come in many different sizes. While some of them are relatively large, the trend is to use smaller components in today's surface mount designs. Their size is described by a 4-digit number. For example, 0805. The first 2 numbers represent the length of the component. In this case, 80 thousandths of an inch. The last 2 digits represent the width of the component, or 50 thousandths of an inch. Some newer chip components are as small as 0201, or 20 thousandths of an inch by 10 thousandths of an inch, and 01005, or 10 thousandths of an inch by 5 thousandths of an inch. Pointed tips, such as the conical tip, are used to transfer heat into a small area. These tips should be used with small lands and components that need very little solder and have minimum thermal mass. A chisel tip will transfer more heat because more of the tip will contact the parts to be soldered. As a general guideline, the width of the tip should be slightly less than the diameter of the land that's being soldered. Every solder connection should be completed in the shortest possible time to prevent excess heat from spreading to nearby areas of the board and causing thermal damage. 3 seconds should be the average time or dwell time to complete a hand-soldered joint. If it takes more time than that, you may be causing heat damage to the board or the component. The amount of time solder takes to solidify can also affect the strength of the solder joint. While the solder joint is cooling and the solder is not yet solidified, any bump or vibration can break, loosen, or otherwise damage the electrical and physical properties of the solder. Another variable is the flux contained inside the tin lead or lead-free solder wire. Most of the solder alloys used for hand soldering have a core of liquid flux. Flux cored solder is like a tube that releases liquid flux. Flux has 3 main purposes. Once the flux is heated and activated, its primary job is to remove light oxides or contamination from the metal surfaces to be soldered. The metals to be soldered may look perfectly clean, but most metals will quickly oxidize whenever they are exposed to oxygen in the air. You might think of flux as a special kind of soap that removes oxidation or cleans metal so that it can bond properly. The second job of the flux is to prevent the freshly cleaned metals from being re-exposed to oxygen in the air in order to keep the surfaces from re-oxidizing. The liquid flux will cover or protect the freshly cleaned metal until the flux is displaced by the solder. The third job of the flux is to assist in the transfer of heat from the tip of the iron to the metals being soldered. The hand soldering operation usually happens very quickly, and it's impossible to see everything that's occurring since the parts are very small. So let's examine an animated hand soldering operation to observe how everything works. First, the tip of the iron is applied to the junction of the land and the lead to be soldered. This starts the heat flowing. Next, a heat bridge is formed by touching the solder wire to this same junction. This starts the flow of the flux and the initial melting of the solder. The flux moves away from the heat and ahead of the solder, over all of the metal surfaces. The heated flux removes oxidation or contamination from the metal surfaces. Everywhere the flux touches, it helps to heat up the metals. All of the metal surfaces need to be at the proper temperature or the solder won't bond properly. Now the solder wire is moved over to the opposite side of the land, while the solder and flux continue to melt. Liquid solder will move toward the heat. That's why you want the solder to flow from the opposite side of the heat source. Otherwise, you might not get enough solder to flow over onto the unheated side. The flux is pushed along by the solder as it performs its cleaning job. As it moves in front of the solder, it also floats away the loose contaminants. The flux and oxides will end up pooled around the edges of the land after the soldering operation is completed. Now the solder is chemically bonded or wetted to the land and lead just below the surface of the metals. Surface mount technology, or SMT, is almost always associated with high-tech automated assembly processes. Let's review the basic SMT assembly sequence. First, solder paste is typically applied to the lands of the circuit board using a stencil printer. Newer technology allows solder paste to be dispensed directly onto the circuit board without the use of a stencil. Then the components are precisely positioned on the solder paste using one or more placement machines. The faster machines, also known as chip shooters, place the smaller chip components with machine gun rapidity. The slower machines, also known as pick-and-place machines, install the larger, more complex components, such as quad flat packs or QFPs, plastic leaded chip carriers, or PLCCs, and ball grid arrays, or BGAs. Last, the components are soldered to the lands on the circuit board using a reflow soldering process. As a general guideline, the width of the tip contacting the work should be slightly less than the area of the land that's being soldered. The first step is to apply external liquid or paste flux to the land where we'll be making a solder prefill, also called a solder bump. External flux should be of the same type contained in the flux cord solder that's being used. Now we'll tin and clean the tip. Then we'll add enough solder to the prefill land to create a slight crown shape. After cleaning the solder prefill, we'll use flux to clean any oxides from the land and to improve heat transfer during the soldering operation. Next, we align the component in the correct position on the lands. Notice that the pre-filled land will slightly lift the component off the board. Now, hold the component in the alignment position with a wooden stick or tweezers so the soldering iron won't push the component out of alignment. Then, apply heat to the pre-filled land. The solder will melt and the component will drop down onto the land. The solder will wick up onto the termination to form a fillet based on the amount of available solder from the pre-fill. The last step is to remove the soldering iron and wait a few seconds for the solder to solidify before removing the holding tool. The size of the flux cord solder wire is an important consideration when soldering small components. If the solder wire is too thick, it's easy to melt too much solder into the joint. If the solder wire is too thin, it can take too long to melt the optimum amount into the joint. Next, after adding flux, we'll solder the second termination to the land. The tip should contact both the land and the termination while the solder is added to the opposite joint. Be sure to add just enough solder to form a proper fillet. After both sides are soldered and cooled off, the flux residue should be cleaned with the proper solvent to keep it from hardening, unless no clean fluxes are being used. In that case, cleaning is not required. Soldering iron tip oxidation occurs naturally when the iron is exposed to the air during the soldering process. If the tip is oxidized or contaminated, the solder will not stick to it. This is known as dewetting. Flux is used to clean the oxidation from the tip so that when solder is applied, it wets to the iron tip. When oxides form on a soldering iron tip, the tip performance is degraded. Oxides create a barrier that decreases the heat transfer from the tip to the connection. If the tip is not cleaned and tinned before putting the iron into the stand, the oxides can build up and render the tip unusable. Tinning the tip is the best way to combat oxidation. The tinning process begins with the application of solder onto the working surface of the hot soldering iron tip. The solder coats the tip, forming a barrier that prevents oxygen from reacting with the tip. The flux in RMA cord solder improves this tinning process by breaking down any oxides already present on the tip and allowing oxides to float to the surface of the solder. Proper tip maintenance involves one of two methods: either wiping the tip on a slightly damp, sulfur-free sponge, or dabbing it on a brass pad made specifically for hand soldering. After wiping the tip, always apply a fresh coating of solder to the tip before placing the iron in the holder. On fluxes that require cleaning, the general idea is to remove the flux residue right after the hand soldering operation by brushing the area with the appropriate cleaning solution. Your company will select the right cleaning fluids, which may be water-based or solvent-based, depending on the type of flux being used. This cleaning operation should always be performed immediately after the hand soldering operation. If it's not done right away, the flux residue will harden and become very difficult, if not impossible, to remove. An absorbent, lint-free, and ESD-safe tissue is often used to remove the solvent, so the residue doesn't just spread around the board.